Hello. In the previous video, we have sketched the graphs for a bouncing ball, assuming that each bounce is elastic, meaning that there's no loss in kinetic energy during the bounce. How would the graphs look like if the bounces are not elastic, meaning that there's a loss in kinetic energy during each collision with the floor? As usual, let's start with the VT graph. So we start from the ball being dropped, so the velocity starts from rest, and so it speeds up on the way down and then hits the floor and rebounds. But this time around, because the collision is inelastic, it's going to lose Ke, so it's going to rebound with a speed that's less than the speed at which it collided with the floor. The velocity is not going to rise back up all the way, but it's going to rise up maybe somewhere here. And so now the ball is going to lose speed as it rises, reaches the peak, and then accelerates as it falls back down. And then it gets the next bounce, and so on. Now, what are the key features of this velocity time graph? Firstly, after each bounce, the speed becomes reduced. So look at the upward speed here. It rebounds with an upward speed that's less than the speed at which it collided into the floor. So same here, the rebounding speed is less than the colliding speed. Same here, the rebounding speed is less than the colliding speed. So that's number one. Number two, all these straight line segments here must be drawn with the same gradient. After all, these are the parts of the motion when it's free falling through air. And we know that when it's free falling through air, the acceleration is always the same, negative 9.81 meters per second square. Thirdly, the speed at which the ball falls back onto the floor must be the same as the speed that it rebounded off the floor. So this speed here must match this speed here. And this speed here must match this speed here. And same here. These two are the same. And these two should be the same. And this also means that the rise time and the fall time must be the same. So this rise time and fall time are the same. This rise time and fall time are the same. And so on. Now that we have our VT graph, we can figure out the acceleration time graph. So the acceleration is going to be negative 9.81 meters per second square all the time, except during the collisions. During the collisions, you have a very large positive acceleration. Just by drawing the VT graph in a disciplined manner, we can make the conclusion that the bounces get closer and closer together. I'm sure that tallies with your real life experience watching a ball bounce and the bounce getting closer and closer together. Now for the ST graph. Obviously, it's going to rebound to a lesser height than before as the energy is sapped away during each bounce. There's another thing you should pay attention to when sketching your ST graph. Remember, the gradient of the ST graph represents velocity. So the gradients here and here and here, notice that the gradient keeps becoming smaller and smaller. So that makes sense because your velocity is getting smaller and smaller after each bounce. And so we're done. Ta-ta!